Okay, so hello students, today is May 19th, okay, and we're going to be reviewing some basic concepts on oscillation of systems with several degrees of freedom. And hopefully we will be able to explain more or less what you have to do for the first homework so you can start it. It's yeah, that's basically it. Please don't forget, if somebody is interested in the class notes, hopefully by the weekend I have completed the draft. So I'm reviewing the draft. This morning Giovanna helped me with some of the chapters, and hopefully over the weekend I will send it to somebody who's going to make the copies. So I need to know how many copies we need to make. If somebody is interested, so please send a message to Giovanna. And you have until tomorrow, that's the deadline for to let me know if you need a copy. It's not obligatory. One more time, it's not obligatory, but it may be helpful. It's a combination because I didn't have enough time to translate everything to English. So you'll see that there are some parts in Spanish and then some parts in English. But anyway, I think it can be of a lot of help. Okay, so let's go on with this thing. And then Giovanna, can you see my full screen?
Yes,
Giovanna,
I can see.
Can you see my full screen? Okay,
Yes, go ahead.
Thank you. So this is what we mentioned on Tuesday. So it says that we have oscillations. We have this long equation, and we could differentiate two types of problems. Okay, we can talk about free oscillation or forced oscillation. In the case of the free, we're interested in the natural frequency. Okay, and we could include or not damping. In the simplest case, we do not include damping, and this is an expression for the natural frequency. I think somebody helped me remembering this expression, and that's it. Okay, now here, in the case of the damped case, this term is very important. Okay, that means that this solution dies out. Okay, and this term, okay, includes this zeta term, and this depends on the amount of dissipation of energy. Okay, the problem with that is that there's somebody in the waiting room, Giovanna. With this is that it is very complex to determine. One more time, very complex to calculate. Okay, but we need it. Okay, if we do not make a good estimation of the damping, okay, remember that the wrongly deduced that the amplitude of forced response is infinite, which is never true. And one of the reasons is because we are not including damping. So this is very important. So remember, using this concept, we could determine the Z constant using decrement, logarithmic rate decrement. Okay, that's there. Now let's continue. What happens when we have forced oscillation? Okay, in this case, we have excitation. So we have all terms, the full equation. And the thing is that I'm going to write it again here. The excitation in this case is going to be equal to an amplitude of excitation. And then we have e to the I omega t plus a phase shift, which is beta. Now, here since this is an unhomogeneous differential equation, the solution, for example, W, will be composed of two parts. The first one is the homogeneous part. And the homogeneous, remember that it's basically the solution of the homogeneous is the solution of the, oh, Jesus Christ. Oh, Jesus. We think here, this is a problem. That's there, okay. So this is the homogeneous solution. And the problem with this is that this dies out, decreases in time. And we have a particular solution, which is steady. So this one here is transient, and this is steady. Okay, and this is the one which is of interest for us, because this one here, since it is transient, that means that it will die out, and in some cases it dies out very quickly. So this one is steady, and this is the one which are of interest for us. So this one here has an amplitude. This is the amplitude of the response, and then we have e to the I omega t plus beta. This is the same as this one, but we have in general a phase lag. That means that the response, okay, takes some time to respond to the system, the response of the system, okay? That's typical. And the most important part here is that this omega is the same as this omega. For me, it's like a signal, okay? If the excitation has a certain frequency, that parameter is reflected in the response. The response has the same frequency. When you analyze a vibratory problem, one of the first things that you have to do is to identify who is exciting. You have to remember this. So what you do is you put a sensor, for example, an accelerometer, on the system which is vibrating. Take that signal and analyze it. Do a Fourier analysis, something like that. And from there, you can identify the harmonic, which has the largest amplitude. That's the one which is causing the problem. And then you see down in the axis, you read the frequency. And through the frequency, you go back and say, okay, there must be an excitation which is producing this response. And through the frequency, you identify the excitation. That's the first thing that you have to do. Once you know who is causing the problem, you can start going on and trying to see what you can do. Okay, so that's extremely important. Now, this is the amplitude, of course. This is something that we are very interested in, and this is the phase shift, which is also of interest, especially in the laboratory. In the real world, it's very difficult to measure. So here, W. If this is very large, something could break. So we have to do something. We have to solve the problem. And that means that we have to reduce W, the amplitude of the response. Okay, now, before we go on, let me go back here. I'm not going to include here the expression for the W. You can recall from your class notes, okay? Do you remember, anybody remember the expression for W? Matute, do you remember the expression for W?
Sorry. Good afternoon. Is F over K over square. Okay. is the denominator is complex.
It's a very long expression.
Exactly.
Okay, Jimenez, go on. F over K divided by the square root of
Square root of 1 minus the ratio between the frequency excitation over the natural frequency, a square,
okay,
plus
square
2 the damper coefficients per
times
and frequency.
omega over omega 0. Yeah, and that's square.
That's
Okay, so it's a very long expression. You are responsible for recalling, reviewing how to deduce that. I mean, how you get up to there. Okay, and also you are responsible for using it. Okay, so you have to be careful because it's a very long expression. Okay, and how about the phase shift? Those, Miss Freire, do you remember the expression for theta for the phase lag of the response? Is the inverse tangent of what? Do you remember?
Of the
No. I can help you. Minus. There is a minus in the numerator. Minus.
It's minus the frequency of the damper over K over
minus 2z omega over
2Z.
omega 0 divided by
1 minus omega divided by the natural frequency
0
to the square.
Square, yes. So that's, see, one a very interesting thing is that the denominator could be 0. That means that in that case, theta would be 90. And that's when you have resonance, okay? Now, again, if the natural frequency gets closer to, the excitation frequency gets closer to natural frequency, there is a difference in the denominator who gets to 0 or approaches to 0. That means that the quotient increases and you have an increasing response. That's resonance. That's something that we have to avoid. We have to be very careful. Okay, so all of that is, you have to review for the homework. This is just a review. I'm not going to do it for you. Okay, let's go on. Now, this is something which is very, very important, okay? And we're going to use it in this course, okay? When we apply the Newton's second law with rotational motion, okay? This is a general expression. This is from your course in dynamics, okay? So we have a system here, of a point here where we have the centroid of the mass, okay? And let's suppose that we are working in the plane, okay? So we can have a point P and we can pass an axis through that point. And this axis is orthogonal, it's perpendicular to the plane of the paper, okay? Now here, we could have several forces in any way. And here we can apply this expression in order to calculate the response of the system. Okay, so this summation means that you calculate the moment of each one of these forces considering an axis which passes through this point. For example, this one here will have, you can draw the line of action here, and this is going to, if this, let's call it Fi, this would be R sub I, and the product will be one of the MP1. And you have to do for all the terms. You have to be careful with the 6 signs, positive or negative. So that's this one here, M sub P, that's this one. So you have to consider all, in this summation, you have to consider all the forces acting on the system. Now this term here is very interesting, okay? I have, this is a cross product, remember, this is a cross product. So this is a vector relationship. Rho C is a vector which goes from P to C. Let me change color. So let's go green. So this is rho sub C. That's rho sub C. Okay, so it's a vector that goes from P, the point where you are considering all this as a reference, to the centroid. M, of course, is the total mass of the system. R double dot, that's the acceleration of point P, okay? And JP is the second moment of inertia of the mass distribution. Okay, that means that, for example, here I have one mass. This is a small mass. So I set up an R, a distance here. And this JP can be calculated, integrated over the whole domain of R squared dm. Okay, so you have to add each one of these. Okay, so this has units of m mass times length squared. And of course, this is also a vector, theta double dot. This is a rotational acceleration of the body. Okay, so this is the general expression. Now, there are two, well, I insisted that this is a vector equation, so we have to be careful. Usually in our course, we work in the plane. So every vector is perpendicular to the plane, so it goes in the k direction. Okay, so that makes things a little bit easier for us, right? If we were in the space, for example, the people in working with these satellites, that they are in trouble because they have 6 motions. So they have to consider 3 rotational directions in order to calculate the acceleration is the 3 directions. In our case, we consider that the motion is in the plane. So this equation is basically has the direction, every vector here has the direction perpendicular to the plane. So it's a little bit simpler. So we recognize that and we said, okay, we take just the k outside the equation and we go on only with the amplitudes. Okay, so it's a little bit simpler. Now, there are 2 special situations here that we usually apply. One special, oh, Jesus, come on. One special situation occurs when P coincides with C. Okay, if P is in here, in this case, this vector would be 0. So in this case, rho sub C would be 0. So in this case, we wouldn't have this term here. The other situation occurs when P is fixed. In that case, R sub P doesn't move, right? Because I mean, it's fixed. See, if this point is P is fixed, it doesn't move. So it doesn't have velocity. If it doesn't have velocity, it cannot change something that doesn't exist. So the second derivative is more than 0. It's 0. Okay. So in this case, this term disappears, is equal to 0. And again, this term here disappears, and we have only this summation of moments and the right-hand side. So these 2 special situations we can apply quite often. In the general case, Okay, we have to include the three terms. And that's going to be our situation when we work in chapter 3 in the ship. Okay, because in that case, we're going to pass an axis through midship, right? And usually the center of gravity in the ship, center of mass of the ship, is not on midship, usually aft. So rho C is not going to be 0. Now the midship is moving. So R sub P is not 0. So we have to include the three terms. Okay, it's not that complex, but we have to be sure that you can apply these situations. Okay, so let's go on this case. Okay, now let me, if we consider point O as our reference point, so we can say that summation of moments O, in this case, R sub P double dot is 0. So I'm not going to include it. And this is equal to J0 double dot. So if we say that this is X, this is Y, and this is Z, this is K, all vectors will be in the K direction. So we say, okay, this is the positive direction. You see it's in this direction, which is positive. This is the positive direction. And in here, we have this force, mg, and another force here, fx, fy. Okay, so we're passing an axis through this point O, which is fixed. So these two forces, they don't have arm. So they do not contribute to our summation. Okay. Now, the only force is this one here. That's the force which causes the restoring effect. And we see that this force generates a moment which is the opposite, in the opposite direction as this rotation. So it's going to be minus, the force is going to be mg, and this is going to be from here to there, that's going to be the arm. So it's going to be L sine of theta. On the right-hand side, we have J0. So we make an integral considering distances from this point. We remember that this is a string which has very low mass, neglectable. And this is a point mass. So the dimensions of this ball are very small. Okay, so if you consider the R, the distance from 0 to any point on the ball, basically is constant. Okay, so see, if I consider this piece here or that piece here, basically there's no difference because the dimensions are so small. So basically the length of R is basically L. That means that the integral for J0 gives us, remember, M L squared times theta double dot. From here, you remember that you cancel M, you divide by L squared, and that's the equation. Theta double dot plus G over L sine theta equal to 0. The second case, center of mass, we put it the control at the center of mass and here. So we said summation of the moments with respect to point C. So right there, rho sub C is 0, so it's not going to appear. And that's going to be minus 0, and it's equal to JC times theta double dot. All of this equation is multiplied by K bar. Now, in this case, what moments are you going to have? Well, if you pass an axis through this point, of course, these two forces will have arm, and we have to consider them. So we have to do summation of forces in the x direction equal to mass times acceleration in the x direction. We have to do something similar for the y direction. And then we have to combine the three equations. So I'm going to just sketch the solution. I'm not going to do the details. You have to do it. So we can say the moment, this is the positive direction. So Fx produces a positive or negative moment. Somebody? Fx produces positive or negative? Mr. Galarza? Fx,
Negative.
Fx,
Negative, doctor.
negative. So it's going to be minus Fx, and the arm is going to be from here to here. So that's L cosine. Fy produces also in this direction, so it's going to be minus Fy, L sine of theta. The weight does not have arm. And how much is JC in this case? Ms. Sayo? How much is JC in this case? J sub C. Sayo?
It's only M.
J sub C is the integral
The integral of R.
R
R
squared.
squared.
But the problem is that, remember, the dimension, the diameter of this, whatever, it's a little ball. The diameter of this is very small. So R squared is very small. In the limit is 0. So that's one equation. So we need to do summation of forces in the x direction. It will produce the mass times the acceleration. I have to insist on this. This is the acceleration of the mass of the centroid in the x direction. It's not just an acceleration. It's the acceleration of the center of mass. That's the second equation, Newton's equation. So in this case, we have to be careful because if we have this is the string, this is the mass. There are two accelerations here. One is this one here. This is a tangential. So it's going to be L theta double dot. There's going to be a radial. It's going to be L theta dot squared. Okay. Here, this is theta. So this is perpendicular to that. This is perpendicular to that. So this is also theta. And in the vertical, if I put this axis here, this is also theta. Okay. So we have components. So what's the forces in the x direction acting on the system? What forces in the x direction acting on the system? We have only one.
Fx.
Exactly, that's all. And the mass times. Now in the x direction, we have, I'm going to write it like this, see? This is the tangential of C. So it's this one here times cosine of theta. And here, this is the radial C times sine theta. and you have this expression, you can replace it here. And in the other direction, you do the same. So it's the acceleration of the center of mass in the vertical direction. What forces do we have here in the y direction? Zambrano, what forces do we have in the y direction?
Fy and the weight.
Yes. And then they are not going to be equal to each other. So we're going to have mass. So we're going to have A TC, which is this one here in the vertical direction. So sine of theta. And we're going to have this one here. So it's going to be plus radial of C cosine of theta. So we can take this to the right-hand side. This here, we put both into here and we go on and we should have the same equation. Now let's go through the last one, which is more interesting before we go to the break. Okay. In this case, let's put here in point P the reference system. So let's call this distance from O to P, let's call this distance A, and from A to C, we call it distance B. Okay, now, in this case, it's much more easier. I'm not going to do it in detail. So you have to, after class, you have to do some effort, okay? Let me change color, just in case. Let's go green. Okay, now instead of working in X and Y direction, I'm going to work in R, radial and tangential directions. Okay, so here. So this is the third case. P, the reference. Well, it's not the reference, it's the point through which I'm sending an axis to consider all of these rotational actions. Okay? Now, in this case, P is not fixed. P does not coincide with C. Now, in this case, we have to write rho sub C, and we're going to write it like this. See, rho sub C goes from here until here. So it's rho sub C. So I'm going to write it like B. And since it has direction, I'm sorry, it has vector component, vector characteristic, I multiply by a unit vector in the R direction. Now let's see if we can draw R sub P double dot. Again, you see that this point here, okay, has component in this direction and also in this direction, similarly to this case. So tell me, how can you write, I don't know what my pointer is. Oh, here. Okay. Anybody? What is equal to R sub P, acceleration R sub P?
Yeah.
How about this one here? This is the tangential.
Acceleration.
Yeah.
Yeah.
Give me a value. How do you express this component? What would be the amplitude of this acceleration? This is tangential acceleration. The distance from here to there is a. It's rotating. So I have this point here. It has an acceleration in that direction and also in the radial direction. So in the tangential, it's similar to what? To this value here. See, this is a tangential acceleration of the mass. In this case, I'm looking for the tangential acceleration of point P. What would be the tangential acceleration of point P? Delgado. Okay, it's going to be A times the second derivative. And remember, this has to be vector. So we put it, this is tangential vector in the theta direction. That's in this direction. That's radial, that's tangential direction. How about this one here? This is the radial component of the acceleration of point P. Which is that? Miss Pinkai. How much is this one, this component?
I think it's A times theta dot square
Direction?
J.
I sub R, because in the radial direction. Sense is in this direction or in that direction. It's negative. It's negative. Okay. So with this, I'm not going to solve it. You have to do it. Now, in order to complete, we have to do the moment. So here, we have to assume, since we do not the reactions up here, okay, we have to consider, okay, that there is a, let's call this one, it's going to be, let's call it F theta. That's the force in the reaction in the tangential direction, right? This is positive, this is positive. We do not know how much that is. We just put it there. And finally, we need a force in the radial direction. This one here, F sub R. Why in this direction? Because that's the positive radial direction. We do not know how much that is. So we just assume it as positive. Okay. So we can say that summation of moments with respect to P minus rho sub C cross M R sub P double dot is equal to JP times double dot vector. Okay. Now in this case, you have FR is not going to produce any moment because it's aligned with point P. Force F theta will generate a negative moment because it points in this direction. Similarly with mg, remember you are considering the moments with respect to this point. And this is your reference system. So this is going to make you also rotate in the clockwise sense. That's negative. So you have all the components. Now the problem here is that F theta F theta has to be included. And the problem is that you don't know how much that is. So in order to evaluate that, you do summation of forces in the theta direction is going to be equal to what? It's going to be equal to M A sub C in the theta direction. Remember, this is Newton's second law. Summation of forces in this direction causes an acceleration in the same direction of the center of mass. Question for you before we go to the break. How much this is? This is. Hydro, how much this is? How much is the acceleration of the center of mass in the theta direction?
Not very sure. I'm sorry.
Not sure? Anybody? Lopez, do you have any idea how much A sub C theta is?
Is zero? Zero.
No, it's moving, it's moving. See, remember, this is the center of mass. This is the center of mass of system, so it's moving like this.
ML squared over 12.
No, that's the sectional of inertia of, no, in this case, it's the acceleration that I'm looking for. Acceleration, only acceleration. It's here. This is the acceleration of the center of mass. This is the center of mass because the string has very low mass. So this is just L theta double dot. So here we have F theta, okay, is this one we are trying to determine, and there is a component of mg in this direction. What's this component? So it's going to be minus mg sine of theta. So from this expression, you get F theta. You plug it into here. Be careful with these products. And at the end, you make a simplification and you get exactly the same equation. Let's take a break. Giovanna, why don't you stop the recording? Let's take a 5-minute break. Okay, 5-minute